Good morning, I'm Rami Haider and I am gonna be presenting paper 9, which covers the topic of America's Cup downwind sails and the effects of wind speeds and direction on sailing. So as a brief history, the America's Cup is the world's oldest international trophy in world sport, predating the modern Olympics and the World Cup. The first race was organized by the Royal Yacht Squadron in 1851. It was called America's Cup because the first yacht to win the first competition was a yacht called America. Now it's a sailing competition based on match racing. Since its inception, the competition has been limited to the current holder of the cup, which is the defender, and the challengers. The cup is one of the most prestigious, fierce, and controversial sailing competition in the world, with just one winner and no runner-ups. So the cup basically consists of match racing, which is where one boat races against just one another, unlike fleet racing, where several dozens of boats or more might race together. So how does the competition work? Each time the cup is defended, the current holder gets to host the competition. Not only that, in large part they get to set the rules too, so any challengers have to beat them largely on their own terms. Any other teams that enter are challengers and they must all reach each other in the first round, with the top 4 challengers proceeding to the next round. They will then compete amongst themselves until eventually one challenger remains. This last challenger then races against the defending holders of the cup over a series of races. The most winning team wins the cup and holds the next defense. So speaking about sailing terms, since America's Cup and Louis Vuitton Cup, the Challenger Series yacht races, are simply a series of windward and leeward legs, it's essentially to know what's a windward side of the boat and what's a leeward side of the boat. The term windward simply means towards the wind, and leeward means away from the wind. For example, the windward side of the boat is the side where the wind hits first. The opposite side is the leeward side. So the wind pushes against the windward side, which fills the sails and creates a wing-like curve. The leeward wind sticks to this curve on the other side, which creates the pressure difference. So what does a single race between two boats consist of? So before the start of each leg, the next mark is placed exactly upwind or downwind of the previous mark. Then the race starts, where most of the races consist of an initial 3.25 nautical mile beat to the first mark windwardly, followed by 3 nautical mile leeward windward legs upwind, and the final 3.25 nautical mile run downwind to the finishing line. Now it's aerodynamically impossible to get a yacht to head straight into the wind, and so tackling is essential on the upwind leg. However, while it's possible to get a yacht to head straight downwind, it's generally better for the yacht to head off at an angle. This situation is illustrated schematically in the figure to the right, where on the downwind leg, the angles sailed are smaller than that on the upwind leg, but these small angles are very significant. So speaking about analysis of the boats, numerical codes are widely used for testing, but the procedures and the results are not easily disclosed. This is generally due to the excessive secrecy of the high-performance sailboat industry. There is a lack of information to validate new codes and the methodology that designers may use. Most of the publications of reference provide qualitative results instead of quantitative values. Moreover, commercial numerical codes are not specifically developed to study the aerodynamics of sail. There are some difficulties such as the analysis of lifting surfaces without thicknesses and complex geometry of the rigging and the elasticity of sails. So how does a sailing yacht navigate with a constant speed? This phenomena is the consequence of the balance of the aerodynamic, hydrodynamic, buoyancy, and gravity forces. These forces in turn depend on the wind strength, the shape of the sail, type of rig, and control gadgets. In addition to that, they depend on the size and the shape of the hull, displacement of the boat, and distribution of the weight, and finally the sea conditions and the crew's level of expertise. The easiest and most common method to study the balance is to consider the forces acting separately and then include the effect among them. As you can see in the figure, the components of these forces are illustrated, as well as the moments produced. So we can conclude that the driving force is equal to the water resistance, the horizontal heeling force is equal to the horizontal side force, the vertical aerodynamic force is equal to the vertical hydrodynamic force, the aerodynamic pitching moment is equal to the hydrodynamic pitching moment, and the heeling moment is equal to the Reichs moment, and finally the aerodynamic yawing moment is equal to the hydrodynamic yawing moment. The difficulty arises when determining the components of these forces. In our case, the problem is focused on the aerodynamic force, which depends not only on the wind strength, but on the sail, the rig, mast, and hull. But we're gonna be mostly focusing on the wind speed and directions effect. So when speaking about sailing, it's important to highlight the difference between the apparent and the true wind. If you ever watched an America's Cup race, you can sometimes see that the wind could have a speed of 15 knots, for example, and yet a boat can achieve speeds of about 40 knots downwind and up to 25 knots upwind. So how do they do it? Taking into consideration the new technological advancements applied in new boats, which reduces drag significantly by introducing foils, we can see that the limitation on boat speed is not hull design, as one might have thought. It comes down to the angle that the boat can go into the wind. First, consider this. As the boat goes faster and faster, the wind that the boat feels shifts forward, as you can see in the car animation provided to the right, where the shifting wind is illustrated in white. The wind that the car feels, similarly to a boat, is the apparent wind generated by its own speed. But the limiting factor is how much forward force can the winged sail garner out of the wings from the angle between the boat's heading and direction of the apparent wind. That angle can never be zero, as the boat would be moving straight into the wind, and that's not possible under these universal laws. The lift or forward component of the force to drive the boat forward relies on this angle. Now the following animation to the left shows that the drag force increasing with speed and the acceleration force from the wings reducing. Note that there is a step jump down in the drag force as the boat begins to hydrofoil. Had the drag force equaled the acceleration force before the boat hydrofoiled, then the boat would not continue to accelerate. But this is not our point of focus here. So we can see that the boat's speed can just keep on increasing and increasing upon decrease in the apparent wind angle until the forward component of the force from the wings equals the drag force on the boat. As the boat gets closer and closer to the apparent wind angle, the forward force component reduces. The biggest revolution has come from the introduction of the wing being able to gain lift from closer angles to the apparent wind and in a massive reduction in drag. A typical boat sail consists of a mainsail and a spinnaker and a jinnaker. So what is the difference between a spinnaker and a jinnaker? So to deal with the problems of sailing off-wind, the spinnaker was developed. Made from much lighter nylon cloth, conventional spinnakers fill well in the light apparent winds and are mainly used for sailing downwind. Jinnakers, on the other hand, are similar to spinnakers, but they cannot carry downwind like spinnakers. They are attached to the head and connected to the deck level. They are generally sailed at high downwind angles, called reaching angles, from a broad reach to a close reach, as it will be illustrated in the next slide. So as we mentioned previously, since the aerodynamic force behaves differently depending on the angle between the wind and the boat, it's important to talk about a very important concept in sailing, which is called the point of sail, illustrated in the figure below, along with some techniques followed by sailors. So, when a boat is sailing upwind, the angle of incidence of the apparent wind to the sail is small. The sails are pulled tight to the boat, and the flow is mainly attached. In these conditions, sails act like a traditional airfoil. Now, if the angle of incidence of the apparent wind becomes larger, the point of sail is named reached. In this case, the mainsail is hoisted together with a jinnaker or a spinnaker. The flow is more complex since there is a large-scale separation. Now, at highest angles of incidence, the point of sail is called downwind or run. The sails hoisted are the mainsails and the spinnaker. Here the flow is completely detached and becomes unsteady. The traditional airfoil theory can't be applied in this situation. Therefore, the method to calculate the aerodynamic force depends on the point of sail in the study. due to the difference in the behavior of the flow in each case. But where does the aerodynamic force come from? The sails have a profile around with air flows. Due to the camber of the sail, the air on the leeward side has a higher velocity compared to that on the windward side in order to verify the continuity of the field. Now, according to Bernoulli's principle, the high-speed air on the leeward side provokes a reduction of pressure and therefore a suction compared to that on the windward side of the sail. The aerodynamic force of a sail is a combination of the suction on the leeward side and the pressure on the windward side. In the following figure, the flow around a sail is plotted together with the pressure distribution on both the windward and leeward sides. The aerodynamic force is the difference between the two curves, which represent the pressure on each of the sides. Now it can be seen that the major contribution to the force comes from the suction on the leeward side of the sail, as explained previously. Speaking about the wind speed and direction effects, we should speak about the Velocity Prediction Program, VPP, which is a device that generates the boat's speed polar shown below. The VPP calculates the boat's speed in any direction by balancing the aerodynamic and hydrodynamic forces and moments. The data supplied to the VPP program consists of external conditions such as the true wind speed and direction and the force coefficients for various aerodynamic and hydrodynamic forces. These force coefficients are typically determined by wind tunnel and towing tank tests and may be refined by full-scale testing. Now the form of the VPP figure has the true wind velocity as seen by a stationary observer directed vertically downwards, and the angle coordinate represents the true wind angle beta t. The radical coordinate is the achievable boat speed in any direction for a given true wind speed. The figure also illustrates the well-known fact that if a yacht tries to sail too much into the wind with an angle about less than 30 degrees, the drag forces exceed any thrust and the yacht can't move forward. In contrast to the true wind angle of about 90 degrees, the boat's speed may equal or exceed the true wind speed. Now in America's Cup racing, it's not just the boat speed that matters, but also the component of the boat's velocity in the direction of the next mark, which as we speak earlier, it's placed directly upwind or downwind from the previous mark. This component of the boat's velocity is known as the velocity made good, which is the vertical component of the boat's velocity vector. It can be seen that the maximum VMG when sailing upwind is achieved by sailing at a true wind angle of about 45 degrees, and the optimum VMG occurs with a true wind angle of about 150 degrees. This is to a certain extent a compromise between speed and direction. Now knowing that the true wind angle is the angle in the horizontal plane between the boat's center line and the true wind velocity vector measured from the bow, what can we conclude until now? So technically, if a yacht sailed directly downwind at a true wind angle of about 180 degrees, then the apparent wind speed experienced by the sails is only the difference between the true wind speed and the boat's speed. As a result, the thrust is small and the achievable boat speed is low. However, if a yacht sailed with lower true wind angles, then the vector sum of the true wind and the boat velocity results in higher apparent wind speeds and hence greater thrust and boat speed. Now, if the yacht is sailed at too low true wind angles, then the boat speed may be high, but the VMG, which is the vertical component of the boat's velocity vector, will diminish. We can conclude that there is usually an intermediate angle at which the velocity made good is maximized. Now at high wind speeds, the boat speed is in general a smaller fraction of the true wind speed, and the optimal true wind angles tend towards 180 degrees. Now if a yacht sails downwind in the direction that gives the maximum VMG, then the wind experienced by the sails, the apparent wind, is the vector sum of the reversed boat velocity and the true wind velocity. It's the apparent wind speed and direction that determines the forces experienced by the sail as mentioned previously. The vector sum is illustrated in the figures to the right. If you analyze the data contained in the VPP in order to give the apparent wind speed and direction as a function of true wind direction and true wind speed, The results in the following figures can be obtained. Now, going briefly over the results, it can be seen that if a direction is taken such that the true wind direction is near 180 degrees, then the apparent wind speed is very low. As a result, the yacht is able to attain speeds which are similar to the true wind speed. However, if the true wind direction is sufficiently away from 180 degrees, then the apparent wind speed is considerably larger, and the boat can attain higher speeds than the true wind speed. It can also be observed that the apparent wind direction is only greater than 90 degrees for a small range of true wind directions, which ranges between about 180 degrees. This band broadens as the wind speed increases. This result has a significant implication for the type of force that needs to be created by the sails. If the apparent wind angle is 180 degrees, then it's a drag type force that provides the thrust. On the other hand, if the apparent wind angle is about 90 degrees, then it's a horizontal lift force that is required, and the sails need to act more like vertical wings than a drag-producing horizontal parachute. Going into more technical results, if the data is extracted which relates to the direction for maximum VMG for each true wind speed and the apparent wind speed and the direction of the top head and bottom height of the sails, the results are shown in the following figure are obtained. From this graph, it can be seen that as the wind speed increases, so does the boat speed. In addition to that, the optimum true wind angle will increase. Both of these effects help to increase the VMG. Now, at the same time, the apparent wind speed stays fairly constant at the masthead but drops slightly at the boom height. The difference between the apparent wind at the top and the bottom of the sails is due to the combination of the reversed boat's velocity, which is the same in both cases, and the true wind velocity, which increases with height. This combination has an even more significant effect on the apparent wind angle, which will be illustrated in the next slide. So as shown in the following graph, the apparent wind angle is smaller at the boom height, which is the lower portion of the sails, than at the head. Also, it may be noted from the figure that it's only at higher true wind speeds that the apparent wind angle becomes greater than 90 degrees. So if the apparent wind angle is less than 90 degrees, then any drag force will retard the yacht and all the driving force must come from the lift. It's only at wind speeds of over 5 meters per second, which is 10 knots, that the optimum conditions result in apparent wind angles greater than 90 degrees, and drag becomes a driving force. However, even at wind speeds of 7 meters per second, the apparent wind angles ranges from 100 degrees at the boom height to 135 degrees at the head. Throughout this range, it is the lift force that is more aligned with the thrust direction. Since the apparent wind angle varies with height, it's necessary to estimate the effective apparent wind angle. So analysis of a pair of typical sails shows that the centroid of area, as shown in the graph, is about halfway up the 32-meter sail. At this height, the apparent wind angle is about 8 degrees less than that at the masthead. A similar result has been obtained by testing a 115 scale model spinnaker in a twisted flow wind tunnel. This 6x3 open jet tunnel allows realistic modeling of downwind sailing condition by twisting the flow as it enters the test section. In this series of tests, the model sails were tested in both straight and twisted flow. The thrust and the side force results, shown in the following figure, are plotted against the observed apparent wind angle at the head. As may be observed, the results are similar, but the twisted flow results occur at slightly higher masthead apparent wind angles, indicating that the effective apparent wind angle in the twisted flow was between 5 and 10 degrees less than that observed at the masthead. In the next slide, I provided a video of nowadays Cup-class boats, which shows the various components and complexity that goes into developing such boats.
How do the new boats differ from their prototypes? The French team has been happy to lift the lid on what is under the skin of an America's Cup-class cat. Although the new AC-class boats are slightly longer, they take many of the systems and components developed aboard Team's test boats. The wing, pod and crossbeams are the same, as are the hydraulic and electronic circuits. But in a departure from Cup tradition, the new class shares several major elements across the fleet. The hulls are one design, and the wings are so close as to make little difference. This leaves the foils and their control systems as key areas for development. With 40+ knots of wind over the deck, aerodynamic drag is also a big deal, and teams have developed sophisticated fairings. Of the 6 crew, the front pair provide power to control the foils. The middle pair provide power for the wing trim. The helmsman controls the main foil using buttons on the wheel. The big secrets lie in the control systems for the complex networks of electrical cables and hydraulic pipework. And success may well come down to who has mastered this technical challenge the best.
Thank you for your attention.